we buy nanoparticles for $100 package, 25 grams. Okay, it's a lot. It's a lot. But if one day they will not work, you understand?
Okay.
So they will aggregate. So we have glove box. If we divide these particles in 4 packets in glove box in nitrogen, and after we have special machine called puncher. So we put 4 package in puncher and punch 1 package and work 1 day. After 1 day, we have to remove all powder and punch another package. You understand?
Okay.
Because we can work just 1 day after it's aggregate. So So this is what bad situation. So to who move powder, we use turbo pump. Turbo pump take powder, and after it's moved to the aggregator. The aggregator, it's a lot of needles. It's create discharge, cold discharge. And they move in cold discharge, they charge it, and they will, if cluster charge it in plasma, they will be break into small particles.
Right.
After they can be go inside of plasma, can be melted, it can be vaporized. If they have we have just power, total RF power, we have in two antennas. One antenna it's 1.2 kilowatts, another 3.2 kilowatts power. It's enough to vaporize it. Okay. If we have cluster, we have to go to higher power, and we will have a situation. We work with frequencies which permitted. It's like frequency, it's 13.57 megahertz and 27.12 megahertz. But because we have plasma makes some kind of, Kurt will tell, we have some kind of intermediate frequency. You understand? So this intermediate frequency very bad in Santa Clara because you have airport. You can be transmitted. So, but it's good in Fremont. I especially work in Fremont, far from airport. You understand? So, because we have like plasma is good. Like Kurt will understand me. It's like we create like super heterodyne. You understand?
You're just getting at that it acts as a highly nonlinear radiator. Basically, you're putting it at the ISM band at 27 megahertz, and then you get something at the doubling or tripling.
No, not 20. We have 13 megahertz, and we have 27. If we mix in plasma, we have a lot of different frequencies.
Yeah, then
some frequencies can be transmitted by airport, or so we have trouble. So why I moved to Fremont to be not in. I used to work in Santa Clara. I used to work. So, but I cannot work just nighttime. But now Santa Clara nighttime has flight. You understand? Long time ago, I worked with airport. Every time my boss afraid that somebody come to him and punish. So you understand? So this now we don't need to afraid. Now we can start our talking. You
hi, President, by the way.
Yes. Okay.
Hello.
Hello.
Yeah, I thought more people would join. Daniel Tartakovsky from Stanford was supposed to join, and a few people on our side were supposed to join. So I don't know. Let's not wait for anybody and start. So we are gathered today to discuss the grant proposal for the National Scientific Foundation, and let's discuss everybody's contribution and the budget and everything that was the documents that were sent by Yuri, which is the management plan and the proposal, right? So I hope everybody has everything in front of them. If we need, we can also share a screen if needed. So, so Yuri, I want to ask you this question because this is very important for everyone to believe in the project. Why do you think you can win? Why even submit the proposal? What's so special? Where's the magic?
Special is that we have new concept is 4D concept. It means it's like we use 3D, we create material, some energetic materials that can resist itself from high current, and also we build lattice. They can also resist its lattice result, and also we make some kind of architecture that we can also protect solid electrolyte interface layer for here. So we decide a lot of problem. So this system resist and survive during high current, and this system also resist to protect other environment like a solid and electrolyte interface. So we have silicon which increase in 4 times. 4 times. It's a lot of usual material can be damaged. But because we have structure like lattice structure, we will believe that this lattice structure will survive. And also we make some kind of jobs that not just lattice structure survive, but survive also interface, a solid electrolyte interface. Because if solid electrolyte interface will be ruptured, we will lose lithium, and the battery will be exhausted. So this is, project supposed to be end up with some production line. Production line, it means it's like, what is production line? Future manufacturing. You have like raw material from one side, and after on the end you have product and product. One setup, one process, you have product. So you have three tapes go ahead with capstan, 3 capstan, and they go to capstan, downstream capstan. One transportation. But if one can stop move every time and press together 2 electrodes with isolator, with separator, another part can move ahead and can move back. So we have between them some kind of accumulation system which allow to one tape to move continuously, another tape move back and forward until we will have deposition. So deposition, 2 system make lattice from one side, lattice from 2 sides, and after this lattice supposed to be make superposition together and develop piezo capacitor. It's mean we talk about now to make production. We talk just about piezo capacitor, pseudo capacitor.
Yuri, may I interrupt you? I think you're going into way too many details.
Okay.
Maybe we shouldn't go that far.
Okay.
And by the way, I'm very sorry I forgot to introduce myself. My name is Tatiana Kurzner, and I'm CEO of Nanocoding Plasma Systems, and I'm also Yuri's daughter. So let's talk high level, because this meeting is about contribution of each side. And we wanted to hear from you guys. You're from the same university. What made you interested in this project in the first place? And what you hope to achieve? What's your agenda?
So let me I guess I'll just sort of talk on the high level because yeah, Yuri and I talked I think it was what, maybe 2 weeks ago, 3 weeks ago now about this, and from our point of view, I think what we can do is we can potentially provide some students that can work on sort of developing this thing. And on our end, Robert Marks is a material scientist, so he works with you know, different materials, and so there's an interest in some of the research as a potential for advanced manufacturing, which we're also trying to collaborate with other companies on. And then earlier this week, we sort of enlisted Kurt for the, Kurt's a, what are you? You're an Attenda RF person, right?
Mm-hmm. Yep.
Yes.
Yep.
And in order to get somebody in from the electrical engineering end, I kind of talked to a couple of other people, and you know, just in the very quick development on this, we're interested in, you know, helping and contributing to this. Usually at this stage, when we're talking about these proposals, we want to find from our end, how could we contribute? So are we talking about building something that's doing the powder deposition and then interacting with the plasma, or are we talking about something that's trying to do some kind of test on what's produced, or some design of the electromagnetics of this? So my role really was just to kind of Robert and Kurt together for this meeting. In looking at this proposal, I think the limit was about 250,000 per year. And so from our end, we can provide students, we can provide some of the faculty expertise to the design work, development work. But there's a little bit of a, you know, squeeze on the budget because once we start adding students and adding faculty time, it's going to eat into a big chunk of this proposal. So my hope from this meeting is to try to have just some sense of how much of the proposal grant you guys want to go to your company, and how much can go to Santa Clara, and then what could we potentially do with the amount of money we're looking for in Santa Clara. I myself was not looking to take a kind of a major role in this, so I can help either shepherd the project, or I'm also willing to you know, also step aside if we want to put more money into the students or my colleagues, if you know. And this typically happens. Sometimes we get squeezed by the budget, and so we kind of come in and say, okay, we'll put in just a very little bit of faculty time in favor of being able to get a student or have a student, you know, more time for the student to work on this. So that's my kind of view at the high level. Maybe I can have Robert talk a little bit about the material science end, or what
Yeah, I mean,
there.
mainly I'd want to just kind of know specifically what kind of problem we're trying to solve, because Yuri was talking about the agglomeration of the particles, but then it also sounds like there's some kind of actual powder delivery mechanism that maybe needs to be designed. So I'd want to know which one of those, and be able to decide if I think that's something, you know, our students can actually do at campus or possibly your facilities.
I can tell you. First of all, we have two problems with powder delivery. I told it's not just only powder, it's also carbon nanofiber.
Right.
They also agglomerated and put together. So this we have to separate, we have to solve this problem.
You're trying to say, okay.
But this problem solved, I told you, solved with help of Kurt, because this is, we have to create electromagnetic field, plasma, and cold plasma will separate this part, like carbon nanofiber and also separate nanopowder.
And so you're trying to keep the particles dry the whole time.
Yes, but it's not enough. Even they drive, because van der Waals force, they will even dry. They will connect it to each other because they have huge surface energy.
Right,
And
sure,
we have to supply them with negative charge.
Right.
They supposed to be break. You understand me? So
Right.
And who do it?
But when you say like you have a tape machine, are you trying to do something kind of similar to tape casting, or I don't.
No, okay.
Do you know what I mean by tape casting, like traditional?
No, we make printing, but instead of laser printing, we use focused plasma, atmospheric plasma. It's called inductively coupled plasma.
Right. Okay,
this inductively coupled plasma creates huge temperature, 10,000 degrees.
Sure.
No, okay, and a material which go to this plasma, they become melted. We have two stages of torch, two stages system, melted and after vaporized, and after they go to we create thin beam, we can make build structure like lattice.
So one question again relating to the deposition part. Would you be interested in doing this in a slurry or kind of in a take the carbon nanotubes and put them in a liquid? Because people usually put them in a solvent and then sonicate them for a while to get them to declump, and then you could generate a slurry, which presumably if you also hit that with the plasma, that would very quickly, evaporate or burn off.
Okay, but slurry.
All dry. Do it as a kind of wet chemistry.
Yes, but slurry will create for us a lot of contamination first, and second, to make slurry, we have to spend we spend a total 5 kilowatts. So we have commercial very cheap generators, and in this slurry you have to use 50 kilowatts. I did it when I have like such ability. It's huge machine, very expensive. So you can work with slurry, but it will be very expensive.
Okay.
Yeah, so I guess it sounds like a lot of the issues have to do with the particles clumping together. So how does this require, I guess, contributions on the RF and the electromagnetic side? I know you've mentioned it a couple of times, but I skimmed through the proposal and I tried to understand what the objectives were, but what are the gaps you're looking to have students work on, or that my expertise to contribute towards?
Okay. So first of all, we don't know behavior of you see this, like you see each nanofibers in magnetic field, in plasma, it's like dipole. Mm-hmm. How this dipole will be disassembled from another dipole? You understand? This is a very big problem which we cannot decide.
Okay, so I'm imagining you have this plasma, you have a whole bunch of small fibers that have now been separated, and they're under enormous electric and magnetic fields, and you're asking how are they going to behave like small dipole moments, both in a mechanical sense, how are they going to move, and then also how are they going to interact with each other? Is that?
Okay, first of all, you can melt, or you can like vaporize this carbon nanofiber. We don't like it. We don't like it. We have to give such power to make them to charge them, and they're supposed to just be separated from each other. Okay. So we have to make dose of power. You understand? Because otherwise, what happened? They will melt it. They will close. They move in some kind of vessels, in tube, glass tube, and the ref power goes through glass tube, create cold plasma. If they melted, so they will close in. You will have reflected power. because your wall become cannot transport RF power and just reflect.
So you're saying that I am not the most familiar with these inductively coupled plasma systems. I understand the basic operating principles, but you're saying that the gas that you have in here presumably has some of these particles suspended in it, and it's somehow melting and going to the outside and preventing RF penetration. Is that the?
No, we have two types of plasma, atmospheric plasma. One type of plasma I explained. So it's a plasma which can melting and vaporization. It's one kind of plasma. Another kind of plasma, it's just make separation from agglomeration. So
Okay.
two types. Both type of plasma use RF magnetic field, RF electromagnetic field. So one time electromagnetic field create heat. Another type electromagnetic field create they charge in plasma. Also they create some kind of effect inside of because if they we work with metal oxide, which they like isolator, but in carbon nanofiber, it's very good conductor. What happens with this conductor? Each carbon nanofiber like antenna, except here. So what happens in this? We don't know.
Okay. So it becomes the question of, I guess, what are the both dissipative and the field effects of having these small conductive moments inside this plasma? That's
inside. Yes. Well, what is their behavior?
Got it.
It's very important for us.
Got it.
So we have from one side, we create plasma, cold plasma. So they move in some plasma. From another side, they itself accept electromagnetic. They become antenna itself. They become like a vibrator. You understand?
Yeah.
And what happens if they have near another vibrator? What they do? They join together, or they like will be repel each other. This we know. This we have to know this answer.
So I think we're sort of talking about kind of things at two levels. So the fiber or nanotube and the particles. This is more kind of on the realm of fundamental research, I think, right? And then at the very beginning, you were talking about trying to build this as an assembly line process and build these capacitors and do that as a demonstration. I'm a little bit concerned that for a 2-year project that, I don't think we could necessarily do the fundamental and the, manufacturing process end. I think, having the idea of building an assembly line in the future, I think is a good thing. But, the amount of money and the time that we're talking about is kind of a start on this proposal. I think from our end, we might be able to think of some of these fundamental questions and ways to test it and work on that. But 2 years is too short a time to both develop the basic technology and then trying to integrate it into a system. That's my concern.
Yes, I understand that we cannot decide fundamental question with this project. Okay, so first of all, we have to make experimental job. It means that we have to find RF power, which necessary. We will work with trial of error, and we will find such experimental windows, which can allow us to go through what now we have. Bill, please show up. Okay, Bill is.
Bill, can you hear us? We don't see you.
Okay, I have never worked in one of these conferences before, so I'm not sure how to do it. I think
as long as we can hear you, it's fine. Just keep talking.
Well, Bill is handyman who makes such antenna who make such experiment. So because we don't know well theory of this system, we make a lot of experiments. And Bill do it. This Bill prepare like several tubes with antennas, with everything. So we will find such position. We just want to, from Kurt, to go quicker to our decision, to reduce our experimental time. So
yeah, but I mean, I guess I guess this kind of goes back to what Drazen said, though, is that it's does that mean trying to inform the experiments through theoretical predictions or through modeling? I mean, I am relatively a theoretical person. That's where a lot of my expertise is. But I think I agree with the idea that this sounds like a pretty tough theoretical problem to tackle, and you know, let alone in a short time frame with the pressure of trying to actually inform an experimental design. Not saying it's impossible, but like, how do you see that information coming in?
okay, so what I can do? We will have success if we have like small portion of powder, the carbon nanofibers, small portion. Okay, we will have success with theory or without theory. You understand? But if we have low productivity.
Mm-hmm.
You understand?
Yeah.
So we first of all maybe it's okay. You understand? But from production point of view, we have to increase power, increase everything to make good production. Good, we call it feeding rate, because we have to receive deposition rate, high deposition rate.
Mm-hmm.
So, but maybe the system cannot afford. Maybe we'll have some limit.
Mm-hmm.
What mechanism inside, we don't know. So deep, of course, you can make very deep investigation, but on the surface, and it's just first approach, what we need, first approach.
Mm-hmm. Mm-hmm.
Today you have some idea, tomorrow Bill will make your job, what your idea, after tomorrow you have result of what, you understand?
Yeah.
So
yeah.
we can work very fast.
Yeah, and I guess the questions I have are really related to you know, the actual design and what questions that would need to be asked in order to get this thing to work. Because I think the way you describe it, it sounds like there's a number of issues, and you think by turning some knobs, basically by changing fabrication parameters, you can get it to work. But you'd like to experimentally determine what those good windows are.
Yes.
And at least just with my current state of my knowledge, I don't know how I would inform those knobs necessarily. I guess is it do you have a particular vision for what that process would be like?
Yes, of course I have vision. If I have no vision, I will not start this process.
Okay, sure.
So you have like these particles move, they consume RF power.
Mm-hmm.
Okay, they become consume RF power up to some limit. After they disappear, you understand, vaporize it.
Sure.
So we have to limit this power to here. From another side, we have to increase the power because we have to increase our feeding rate.
Mm-hmm.
So this.
Okay, so you want to find the balance there, and just and I think this is getting into the details, and this will be my last really detailed question. But these fibers that you're dealing with, you said you treat them as conductive rods, or you think about them as conductive rods with some dipole moment. Are these semiconducting rods, or is the power so high that any semiconducting effects are negligible?
It's not semiconductor. It's completely like conductive, highly conductive. Highly conductive tube.
Okay, because I know that the different wall structures and the different chiralities sometimes are.
No, we don't care about. We use very cheap material. We cannot use material. So we're not double wallet. Everything just from carbon to make material from carbon. Okay. And we use this material. So they cost maybe $50 for kilogram, you understand?
Okay.
So very cheap material. So, but cheap material, unfortunately, agglomerated. What's this problem?
So let me ask you a question. So in the proposal, kind of at the beginning, there are some pictures of a silicon lattice structure. So, silicon lattice structure, you guys did it in your company?
No, no, this is not company lattice structure. This is structure not for material which not silicon, which not here. It's just guy create from 3D printer, regular 3D printer with like with aerosol 3D printer.
Okay, but you want to do something similar to that.
I want to make similar with plasma because this guy cannot work with silicon. He cannot work carbon with cobalt oxide. No, he cannot work.
So in terms of kind of running this experiment and trying different things, so I guess at some preliminary stage we would run the plasma, run the carbon nanofibers, take some samples, put them under an SEM, look at what the quality is, and then try to narrow down this space of experiments or change to try to see what works.
Yes, yes. This is one type, one part of job. Another part of job we have to build production line.
Okay.
Because we talk about future manufacturing.
So this early work of, okay, let's do some experiments with the carbon nanofibers just to see what the outcomes are, will help inform these questions of where do we need the modeling and where can we better contribute to hone in where we're going. But I think the production line part, even though that's part of pushing these sort of grants and proposals, that might be much farther off because people that try to do these things, usually it takes overcome some of these steps as we go along.
Yes, I understand.
Yeah.
Yes. Okay. For production line, I have to make something. I have to make linear torch. I have linear torch. I have plasma problem for this, for production line. It's production. This plasma problem absolutely different from material science problem. So people can work with material science experiment, which we have machine for this experiment. Another machine we have to work with exactly with linear plasma. Now we have plasma system axial plasma, which we can work make testing everything. But in machine we have we have linear plasma, 75 millimeter long. So we have to make same on this machine. So we will spend time. One team supposed to spend time to find the best solution for nanofiber from everything. But another team supposed to work with industrial machine. We have pilot plan. We have to make from pilot plan industrial machine. So we have two type of job. There
are a number of pieces to this. So how do you envision, splitting the projects or the teams or the funding on this? How, if, like, for example, doing some experimental testing and looking at it under the SEM and trying to kind of figure out what works and what doesn't work, that's a good job for a student.
Yeah.
That's where we could take a student for a year and have, him or her make these measurements and Robert guide that. And then, later phase, we can work with Kurt to try to, do some modeling and try to figure out if the modeling can lead to more insight on this. But again, the big question is how does that fit within the plasma work that you're looking to do, and how much of the work are you looking to do at the company? How much of it are you looking to do with students? How does this break?
Okay.
We need some kind of like structured project. It needs to be for the student. I mean, so that they can ultimately write some thesis about it. Because I'm feeling this sense that like you have this agglomeration problem, and my inclination is maybe to go like kind of conventional ceramic materials processing routes, but if that doesn't work out, we'd want to maybe immediately switch over to doing something more related to playing with the RF frequencies or something which is completely outside my area. So then it's something Kurt needs to work on, and then maybe there's something else that some other faculty member at SCU would be better at than either of us. I don't know. That's kind of what my feeling is right now.
Okay,
That
I will
be able to
find.
provide some kind of structure that they can focus on a few details for some amount of time with.
Okay, so if I were you or your student, so what I do? Okay, so we develop plasma for you. Okay, you put nano powder. Okay, through our system, you change some kind of situation, and after we have like spectra of carbon of cobalt oxide. You understand? Spectrum.
Okay.
You see spectrum, it's like your output. You understand? You have to receive from plasma, you have to vaporize this plasma. You understand?
Okay.
So your student will put plasma, put turbo pump speed, put some power on the we have already our dielectric barrier discharge. We have some kind of Bill, tell me what name of this system which rotate every time. Bill, you hear me?
Which system are you referring to?
A system which we have propeller. What's this system?
Oh, to keep the particles suspended?
To keep in what is like cloud generator. What name you
Right. Well, it just spins around.
Is keep every time powder in cloud. What name of the system?
And it's like a hurricane is what it does. But you guys mentioned agglomeration, and I think that the semiconductor uses
Bill,
ionizing systems to
Bill, look, now
break up that.
Look, we will have think about in future. Now we have to make the detail. We have trip for Robert. We have to tell Robert. We have puncher. You understand? We punch powder package. Second, we have cloud generator to keep powder in cloud. But powder cannot be on the wall because they immediately agglomerate. And after we have turbo pump. And after turbo pump, we have the electric barrier discharge system. And after we have to see spectrum. If we have spectrum in plasma, if we have spectrum, everything intensivity, we will good, guys. You understand?
Yeah.
If we don't have, so we will have cluster. We will bad, guys. You understand, Robert? What is job for you and your student?
I think it's too big of a job. I can feel it.
Hmm?
I can feel it that it's not structured for the students. It's hard to structure for the professor.
No, this is experimental job for student. Very good.
I mean,
why not?
There was some kind of figure in this proposal that just gave like a overview of the whole process and what is going from which step to which, as you just described. I mean, that is maybe something where then I could identify. Yeah, I mean, you're talking about you mean a turbo pump, like a vacuum pump, right?
No, we make from turbo pump, instead of make vacuum, it's become like suck powder from cloud. And
Sure,
move to here. This is just we use turbo pump but Bill create for turbo pump special system.
It's like a cyclone separator. You want to
Yes.
suspended so that they're not sticking to each other and feed into the system.
Because the turbo pump has a lot of blood. They make powder. Maybe they mechanically also crush this cluster. Maybe we don't know what nature of this process, because we what's this like? We work with this process long time, but we don't know natures. Robert's supposed to explain.
So you know, I mean, the difficulty on our end, you know, just to kind of look at the powder, look at the process, do some measurements afterwards, you know, hit it with the plasma. You know, based on my experience, that could be like a 2-student job for, you know, kind of 2 research projects on this with, you know, Robert as a faculty member, or, you know, advising in them or working with them. So somebody on the process end of things, so how do you change the process variables? But then somebody also on a materials end of thing for the measurement and some theory as to, you know, why they're sticking or why they're not sticking under certain process conditions. You know, so that's where, you know, I mentioned that thing at the beginning, which, you know, if we write the proposal to NSF, each student, I don't have up-to-date numbers, but, you know, full-time student is something like $55K a year. Students would be, you know, $110K a year plus some of Robert's time, and so we're already at kind of half the proposal amount, you know, on this. So that's why, you know, we're trying to figure out from our end, you know, where can we plug in to add to the proposal in a way that still makes it, you know, viable for what you want to do at your company. Is that reasonable, Robert?
May you clarify why you need 2 students, not 1 student?
So one probably for the process aspects. So putting the particles into the gas and try to figure out, you know, how they say separated, move through, and then another one for the materials and for the SCM measurements and trying to back up the theory of the materials. But again, this is just a straight, you know, guess or estimate based on, you know, this discussion. But
yeah,
do you want to chime in on this? But you know, this is a complicated process, so it's not just okay, take some stuff in, measure some stuff out, turn a few knobs. You know, we really need somebody on the process end, probably somebody on the materials end, or a little bit more on the theoretical end.
Okay, but what this in result, students supposed to deposit the system on the wafer, okay, and receive carbon nanofiber coated by what this cobalt oxide, and after bring this deposition, bring to transmission electron microscope and see how thick layer of cobalt oxide on the carbon nanofiber. This is the result.
mm-hmm.
This is the result of job.
And what would be a good result of that job?
Good result. It's like if we have like separate carbon nanofiber coated by 100 angstrom of material of cobalt oxide. It's supposed to be or totally encapsulated or partially. We have to decide.
How are you depositing the cobalt oxide? Is it in gaseous form in the plasma?
In plasma, yes, in the fly.
Okay.
So your carbon nanofiber, one guy, move on the plasma in the plasma beam, and vapor go to here is a vapor deposit on the fly on the carbon monoxide in the
and right now you don't have any preliminary results or any kind of sample or material that you've been able to run through yet.
No, we have separately for we have good result with deposition of yttrium oxide. We have very good result. We make deposition yttrium oxide even in small hole of shower head inside. Okay, so we penetrate inside of hole 0.4 millimeters and 12 millimeters deep for applied material. Okay.
Is it your plan to put that in the proposal, like show that preliminary result in the proposal?
What?
You say you have the preliminary yttria result. So,
Yes.
I mean, would you plan to show that in the proposal? I mean, just usually if I if I'm thinking about trying to propose something, I want to say, here's something where it seems to be kind of working, and I want to improve upon it in this way.
Yes, of course, this is characterized that we can work with nanopowder. You understand? If we make the position of on the, but it's for corrosion, plasma corrosion protection. So it's not supposed to be very good. You understand? For corrosion,
Okay.
but for no, its cluster can be making this job because it's like very rough job. But for this job, it's supposed to be a very fine job, no cluster. You understand what difference? Yes. So you have to more careful when you work with nanopowder feeding.
Mm-hmm.
So for point of view, plasma point of view, I make my job. I make thin beam. Now I have to make perfect vapor and perfect carbon nanofiber.
All right. So it looks like Robert just caught a call right now. But so my question to him is really, because I kind of threw this out there in terms of students and kind of process. But could you give some more thought into this and try to figure out what you think you would actually need to have a student work on the manufacturing of the materials end of this? Am I way off, or am I?
Talking me, right?
Yeah.
Yeah, I mean, I could try to read through the proposal more carefully. I mean, honestly, I just haven't had a lot of time this past week, so I just kind of skimmed through it, and I mean, it was a little cumbersome to read in some places. So, I mean, if I sat down and read through this, and maybe I could identify some kind of potential project or something.
Okay.
Yeah.
Okay, so let me tell you.
Go
So
ahead.
student, look, we will create plasma. We will have everything working, okay, our people. But students supposed to make experiment, from routine experiment, to find the best situation, best rate of turbo pump, best what is rate, because we have to make cloud generator, best what else, and also it's for dielectric barrier discharge, the best power applied to from a ref generator.
Okay, so to me that's all fine. I mean, it sounds good, like there's something there, but we also, like, if they're doing a thesis project and they find the best turbo pump rate, they have to explain why it's required, so that there's some kind of academic component to their work.
Yeah.
It's not just like, you know, we played around with these knobs and here we got what we needed.
Yes, it will be good if this student will be work well with CVD in the flight.
So,
It
but
will
then
be
we
perfect.
need some characterization of the materials to, you know, see, you know, what we're getting under certain conditions, and right?
Yes, you will have characterization by transmission electron microscope. This is what you characterize.
But I think that this kind of goes back to the RF power, because that was another one of the knobs that I think experimentally. And I think it's it sounds like, you know, having a student just run experiments or say, hey, I want to sweep power over these points, I want to look at some results and find the best spot. I think that's very doable for a student. For me though, and I think from an advising standpoint, it would then require a lot of theory and academic work, I guess, to justify it as maybe a master's thesis or part of a PhD project. And I think that's maybe, Robert, is that sort of saying what you were saying in a different way?
Yes, definitely. Yeah.
Because I think just the way you described it, I circle it in my notebook, I think it sounds like a very interesting problem, but it's, you know, basically finding the maximum power before these carbon nanotubes blow up or vaporize.
No, not just power, frequency.
But aren't you stuck at the ISM bands? Aren't you stuck using the ISM bands? So 27, 13.
No, we have also low frequency.
Okay, but these are
We have
discrete
low,
values. It's
we
not,
have 330 megahertz, kilohertz, and I don't know. I don't know. Honestly speaking, I don't know what's the best.
yeah, yeah,
You're
yeah.
supposed to answer.
Yeah, and I think it's a cool theoretical problem. I mean, honestly, I think that that's something that could spawn a lot of work. But I think for a student to work on, I mean, that's going to be you know, in conjunction with the experiments. I could see how it could be a small chunk, but I
Yes,
think
yes,
it all
yes.
comes down to what is the structure and what is the
Okay, but before go to experimental, you don't you believe this like you first in the world approach to this time. People make a lot of patent about here, so this we just they have another application, but they find which frequency better for here, which better for here, but they never work with carbon nanofibers. You understand? But they already create this chart. They know, I don't know what's the best, because one people told about low frequency, another people like people in the conference, they argue to each other. You understand? Argue. I don't know where. We have to show experience. Where's the best? High power, the 27.12 megahertz for here, or 330 kilohertz. We don't know. Why we don't know? Because we don't know what electromagnetic theory inside. How this people work? You understand?
Yeah. No, I think I understand the basics.
Yeah, I think that's true. But you know, I think for this meeting, or at least for the kind of hopefully the conclusion of this meeting, you know, the way I usually work is that we kind of define a scope of work. So the scope of what's done at the company, the scope of what's done, you know, with Santa Clara and the students in Santa Clara, and then whether that scope of work matches with, you know, the resources in terms of what we can budget and you know, what we need to hire. You know, and so that's where, you know, like going to Robert and saying, okay, what could you potentially do on the production line or the materials end, or Kurt afterwards on once we have some preliminary data of what we would try to do with the student from a modeling standpoint. I think that is something that we would need to converge on. And then again, I'm a little bit skeptical that this would, in this kind of short period of time, limited funding, lead to a real like production assembly line thing. I think the goal of this proposal is to just demonstrate the proof of concept. That would actually be kind of interesting. You know, proof of concept is used for a later proposal where you try to build it into a larger production line. But I think the separation problem is a problem. I think the coding is going to be a problem. How the carbon nanotubes work in the plasma is going to be a problem. So, you know, as an academic, you know, we define how many different variables or problems we have to solve. And if there's 3-4 different problems to solve, that's a many year project, not a 2-year project. That's my concern.
Yes, look, so if we have, for example, result, not the best result, but we will have total concept or 4D printer, okay? It will be very good, you understand? We don't need to be perfect everywhere, you understand? We will have smell like very, not very good deposition, not very good encapsulation, but we have to show some kind of theory that this is possible, you understand? This is possible. So
yeah,
Robert will tell us, Robert will tell, give us more money, give us more time, we will create. And Kurt will tell also, you understand? But problem is that we have to receive some result.
Okay, so the way I understood it is you guys want Yuri to put together a scope of work for the students, for 2 students.
Well,
right?
I think on our end, you know, we can probably ask Robert and Kurt as well to kind of think about, you know, based on what we've discussed right now, what could we put a student to work on, and what the range of effort is. Is it a full-time student, master's full PhD level? Is it a part-time student? You know, maybe sometimes some of this like process work could be, but on our end, I think we could put together like a very short proposal of, you know, this is what a student could work on. This is how much time we think is relevant. And then that gets folded into the larger scope of work. So is that correct, Kurt and Robert? We can do something like that?
Sure, yeah.
I think that sounds reasonable.
So we can do something like that on our part. But then the question is, you know, how does that fit it within the larger scope of the proposal? And then the other thing that also is a little concerning. So this needs to be submitted through Fastlane?
Yes, supposed to submit it to FAST.
Okay.
Okay, so
And for the sake of this project, Santa Clara would be a subcontractor, but I think you sent me a message saying that, you know, you're asking me whether we could submit it from the Santa Clara end.
yes, we have more probable opportunity to win if you will be like general contractor, what, and the university is supposed to take money because university is supposed to take overhead.
Okay, so then the proposal would be from Santa Clara, and then you guys would act sort of like a subcontractor.
Yes, subcontractor. Yes, we are some contractor. Otherwise, we will not win. You understand?
Okay, so I think there's good news and bad news regarding that. One, I think we could do that, but I think the timeline of talking to our sponsor projects office and then developing an agreement between us and you guys as the company, that I don't think that is going to happen in the near term. I think that probably will take our office much longer to work out.
Yes, I know your bureaucracy very well.
Yeah.
Okay, because I tried several times work with your university in 2001. Okay, so and it was lady Linda.
That was
Linda.
time ago.
Yeah.
She might not be there anymore.
It's very slow process, but I have to prepare everything. So people supposed to be just put in fast line. Maybe we can make together with you. You understand? Without this, without this help of these people.
Okay.
You understand?
Well, it's probably some legal department as well.
Okay.
So from our standpoint, we have to go through them. Linda, I worked with for many years, and then she's since I think retired or left, and there's in the role now. But the bureaucracy unfortunately hasn't gotten any better. We have to submit through them because they're the people that actually have access to Fastlane and that. And so the bad news is that I did not talk to them. I talked to them about us being a subcontractor on this project, but not being the lead submitting the project. So I know we have the capability of doing that, but until I actually talk to them, and my guess is they're probably going to take a long time to work out.
Yes. So
contract between us and you guys, or as part of this. So I haven't talked to them yet. The soonest I could probably talk to them will be Tuesday.
Can I chime in really quick? I'm sorry to interrupt, but I need to jump over to another call for some teaching responsibilities. I guess Drazen and Robert, can you guys keep me in the loop on what's decided on our end? It was nice meeting you all. Thanks.
Okay, one moment. You understand? You are PI. You understand it?
No. No, I think it's too early. It's too early.
That's
but we have to claim you are PI. We all document. I already did it.
I don't know if that's the right thing to do.
Why not?
I think Drazen has some very relevant points in terms of what we have to go through on our end. We don't have an option on how we handle some of these things. So and the time frame of just having it submitted in 9 days is fairly tight. I actually have to run.
Okay, thank you, Kurt.
Thank you.
Okay, thank you.
So I can talk to our office, but we have to submit through our office. There's no other option for us. And then in addition to that, you know, having Kurt and Robert together, you know, they have to work together on this proposal. That's another problem. And the woman who's in charge now, she's not available today, but she will hopefully be available on Tuesday. So I can talk to her at that point, but in the times that I've done this in the past, it usually takes them a while to organize all this to work where we would be a PI and you guys would be a subcontractor. It's easier for us if you guys submitted the proposal and then we submitted as a subcontractor. That was my original understanding was.
Okay, first of all,
it's very hard to win for us. It's very hard. I mean, you need to have a name.
Yeah, I mean, we can submit the proposal. I'm just saying that from our standpoint, the bureaucracy of working it out between us and you in 9 days is I don't think they will be able to do it.
But
there will be no, you know, there will be no from our side. There will be no blocks. It's all going to be.
No, it's all from our side. It's all bureaucracy. I mean, I can talk to them on Tuesday.
Okay, let's do that.
You know,
okay. But approximately how much money you need for this project?
Well, that's what I was asking for Robert and from Kurt to try to estimate what type of work the students would be looking to do. And then we could give that to you guys, and then you guys can look at it and say, okay, this is good. We can work this within the project, or this is too much, and we'll cut back or you know, split it a little differently.
Yeah, I mean, it does depend on kind of the scope of what the student is doing. Like you were saying, if it's a part-time project or a full-year project, I mean.
Okay, why don't you guys decide and let us know, and then talk to your people on Tuesday, whoever you need to talk to, and then what would be on us? What do we need to do meanwhile before Tuesday?
Robert, what do you think? Do you want some? My biggest concern about this is the way I'm looking at the proposal. I think it should be more of a proof of concept and not as much of the full assembly line, because I think that is going to be rather challenging. Yeah, I'd look to Robert and to Kurt to put in what they think they could do with the student to contribute to this project. You guys would review that and come back to us, and I can talk to our sponsor projects office and see if they can pick this up and submit from our end as a lead on the project and what they would need to do to make that happen. But I've worked with our sponsor projects office many a time, and yeah, it's a slow process, unfortunately.
Okay,
so you are very pessimistic about submitting.
Well, for me to be optimistic about submitting at this stage, I would be optimistic if all we had to do was fix some of the writing and change around some of the organization. But I think I want to hear from Robert and Kurt to see what they would propose to contribute to this project, and then we have to come to an agreement on how the budget would break down, and then we'd have to address this administrative hurdle to try to figure out whether we can submit and have you guys as a subcontractor.
Our job will to make assembling. Our job, we will make work with machine. We will not. It's our job. You understand? Machine. Okay. So your job will be what this investigation. Just we talk about.
Okay.
You understand?
I understand that. We're just in a very short time frame, unfortunately, to try to get this through. And what I cannot answer is when I talk to our sponsor projects office, if they come back and say, no, we don't want to submit as the lead institution on this project, you know, I don't have much sway over them if they're unwilling to do that.
How do they make their decision? Based on what?
I think they make that decision based on sort of where the work is done. Partially, I think whoever the lead on a contract is and whoever the subcontractor, it's partially based on what the breakdown is. So if it's 50-50 work, or 60-40, or 70-30, but then the university also tends to be rather sensitive about, and I think, another company or an outside company. So they might come back to me and say, you know, we can fund it if the work's done at Santa Clara, but they may not be willing to subcontract to a outside company.
Yeah, but I don't think it's possible to do in Santa Clara, so that's why.
No, I don't think it's possible to do at Santa Clara either. But this is purely an administrative thing, and
Okay.
purely from a liability standpoint. That I've done some project work with Dymatics that got bought out by Fujifilm. We've done some work with HP Labs, and it was just a big hassle to try to come with some agreement of what work is done at Santa Clara, what work is done at the company, who has to sign this agreement, are people comfortable with signing the agreement? That's beyond my control, unfortunately.
Okay. So the good thing is we're very small, so on our part there will be no blocks.
No, I don't think there's any problem on your part. It's our office. Our office takes some greasing of the wheels to try to get them moving sometimes.
Okay, so let's finish up here and
No, first of all, I have to ask you, what we have to do to make this happen? What from us, our side, what we have?
Well, I have to talk to them first, and then I can ask them that question. So I can ask them, you know, are we willing to submit this being the lead PI, and then you guys be the sub PI? Do we need to have a legal agreement in place between the two of us? How do we split the financial end of it? That the kind of questions that they may have, and then I could come back to you and say, okay, this is what they're willing to do or not willing to do.
okay.
Mhm.
Sounds
Okay.
good. Well, thanks
Okay.
everybody, and
Thank
I
you.
guess there will be a lot more information on Tuesday. And
Yeah. Well,
Okay.
all right.
Thank you.
Have a good weekend, everyone, and
Thank
thank
you.
you very much for joining. Take care. Okay.
Thank you.
Bye-bye.
Bye.
Thank you.